Thank you for the kind introduction. I want to present you a collaborative project that was conducted by me and Jan Schwacher and Benedict Kleiner, handled by Professor Sebastian Müstermann in the Steel Institute at Aachen University with the Marcelo Paterradas and Professor Thomas Wispiski in the ICL at MIT. And this is the outline of my talk. First, I gave you a short motivation and aims, and then followed by the materials description, and I will introduce what is the plasticity and fracture model that we used in this study, and then I present you the experimental program and methodology, followed by results and conclusions. So first, we start with motivation. So due to the time limit, I will give you rather a specific motivation rather than general motivation that why the pipeline or fracture phenomena in pipeline is still very important, although the ONG industry is not at best shape at the moment. The specific motivation is related to actually the UOE process. I think everybody know that in the pipe making process, we normally use this UOE process. It starts with a U forming with such a shape, and then we close it by this O forming, then with a little with welding in between, but then it's expansion after welding. Actually, this process introduced lots of inhomogeneity of the material. Actually, you can see the deformation at here, and here will be a little bit different. And more importantly, it introduced quite inhomogeneity through the thickness, because you can clearly say the material is subject to a bending moment. That means in the inner surface there's a compression stress, and on the outer surface it's a tension stress, and the gradient is also quite different. So this gave us a motivation to study the influence of the thickness inhomogeneity after this process on the plasticity and fracture behavior. And at the same time, due to the same reason, maybe even more due to the prior rolling process, there would be also the anisotropy of the pipe, and we also want to study the influence of the anisotropy on plasticity and the fracture behavior. Well, then we start about the material. We had a X65 pipe from Europipe, and with the outer diameter of 600 millimeter and wall thickness of 19. And we actually cut it the pipe into two sections, or one section like here. So we're focusing on the night lock and with the 45 degree arc, and then we cut it even to 22.5, and from this arc we can produce some plates. You can see from here we characterize the first plate of the outer layer of pipe as top, and follow middle and bottom. The plate has 2.5 millimeter thick and 110 millimeter length. And this is the pipe you can see, and the material actually is completely magnetic microstructure, so very fine structure is found in this material. And the model that we used for the plasticity, we're using the non-associated HEO48 model. The reason for using this is its simplicity to account for both yield stress directionality and R-value directionality. And it gives us freedom to extend it to furthermore to count for non-anisotropic hardening very simply. And basically we have the yield function in the form of traditional HEO48 with the 6 parameters, but we will assume the other 2 LMM, they're just isotropic. So we basically use the force stress of the tensile and biaxial tension test to characterize the categorize the parameters. And for the flow potential, we're also using the HEO48 formulation, but with the parameters calibrated based on R values from the tensile test for 3 different loading angles. And for the damage or fracture model, we're using the modified Moore-Clone model. The modified Moore-Clone model is based, the Moore-Clone model, maybe you know it is the typical plasticity model at the beginning, but actually it gives also some intrinsic finding of the fracture in some sense. So it is just a 2-parameter simple stress-based fracture model criterion, and due to we are characterizing actually for ductile damage or fracture, so it's much easier to formulate this into a strain-based space. So it's the work of Bai and Bisky in 2010, and they transformed this model from the tau sigma space up to a mixed strain stress space in terms of epsilon equivalent plastic strain, and the stress tractility like here, and also the load angle parameter theta bar. And in addition to this C1 and C2, they introduced another parameter called C3, and in this equation is called C theta S, to gain more freedom to adjust this predictive capability of the model. It has not so much to do with the plasticity model, because you could also use a simple misses or HEO to characterize plasticity, but this is just additional parameter to improve the predictive capability of the fracture model. And then we have an experimental program. We started with the work of Kovinani from 2013, and she made a complete study of a pipeline steel with the following program. So it's uniaxial tension sample and followed by some notched tension sample and central hole and butterfly tension and butterfly shear, and also a punch and also some notched long bar. So with this set of experiments, actually we're covering a very large stress space for different stress states. And in addition to the typical work, here we actually focused on the thickness inhomogeneity as presented here. We studied the top, middle, and bottom layer. And also we focused on anisotropy. So the rolling direction, which is the axial direction, and the diagonal direction, and also the transverse direction, which corresponding to circumferential direction. So we had a large experimental program, and in total we resulted in 150 specimens. And this is a quick overview of all the produced specimens or tested specimens. And in this study, we want to give emphasis of the methodology to characterize fracture, because in the sheet metal forming industry, lots of research is done by using the digital image correlation to identify the fracture moment, or by some camera on naked eyes to see the fracture. And for the sheet metal forming, in some sense it makes sense, but for this bulk material, especially thickness, and we actually have the difficulty to really capture the interior damage or micro crack initiation, because when you see the crack from the surface, it's already a large propagation of the crack from the inner surface, so that is giving us a false signal. So instead, we're actually using a direct current potential drop method to give a non-constructive engineering way to detect the internal damage and micro crack initiation. The working principle is simple. It's just basic high school physics. If you have a wire or any metal that can conduct current. If we have a constant current conducted in the sample and the clamping systems, and we know the potential is related to, if the current is constant, the potential is related to the electric resistance, and the electric resistance is actually related to the effective cross-section area. And we can see if there is crack or micro damage initiating in this cross-section, that will give rise to the resistance, electric resistance, and the potential will get increased. So by this principle, we can actually identify, for example, for the NT20, and the crack, the damage initiation phase is long before the final fracture that we see from experiments. And by some interrupted LOM or SEM study, we can also see at the moment there are already a large crack evident in the specimen. And then we give some results of this study. First, we want to focus on plasticity. Actually, first we want to have a look at the inhomogeneity. What is the influence of the thickness inhomogeneity? If we just look at the 0 degree, we can see actually the top layer and the middle layer, they have a very similar flow curve, and even the UPS. But for the bottom layer, it has a much higher stress, a much higher yield stress, and a little bit lower strain hardening rate. And this is observed for both 45 degree and also 90 degree. And actually we can conclude the thickness inhomogeneity is obvious in all angles, but top and middle are similar. The bottom is much more increased. It is related to the highest stress, the highest compressive strain during the UOE process, if you remember. And if we look at the anisotropy, and we categorize top and middle and bottom again. So for the top layer, we don't see obvious anisotropy, but for the middle, there's little, but for the bottom, there's more. So in my opinion, this is related both of the rolling process, but maybe more importantly from the UOE process, because for the 90 degree, we have the bending moment that has a more constraint than the rolling direction, and for the 45 direction is something between the top and bottom. And this is the way how we calibrate the non-associated HO48 models. So we have the R values, we have the stress directionalities, and also the different R values. And we have the yield surface or end flow for top layer, and also for the middle layer, and also for the bottom layer. And then we used this calibrating parameters with, by the way, isotropic hardening law by this constructed fracture models to calibrate a fracture model. And these are the simulation with all the plasticity parameters. We can see we used the 48 NT20 specimen of 0 degree to calibrate our flow curve, and it gave us quite good prediction for the 45 and 90. And here for the fracture study, I'm presenting only the middle layer, and we're still ongoing with the top layer and bottom layer. And also it gives good prediction of the other geometries. And for the butterfly share, here we have some discrepancy that, as you can see here, but for the fracture part, we actually can overcome all this discrepancy at the beginning of yielding. And here is the finally calibrated damage initiation locus. You can see we used 4 different experiments to calibrate the model. And actually at this moment, for this middle layer, the 0 degree, 45 degree, 90 degree doesn't really show big damage initiation anisotropy. It's only a little bit difference. And with this, I would gave the conclusion and the future work for this study. So first point is the thickness, inhomogeneity, and anisotropy are not negligible in terms of plasticity behavior for a X65 pipe steel after UAE process. As we said before, the inner layer shows higher stress compared to the middle and outer because of a high or compressive strain from prior UAE process. And the transverse or circumferential direction shows higher stress than the rolling and also the diagonal direction, also resulting from the UAE process. And the DCPD method was applied to detect the interior damage initiation rather than the final fracture detected by the IC. And in the middle layer, damage initiation does not show very obvious anisotropy. Of course, this has to be checked for the top and bottom layers. And in the end, we also want to further work on the constitutive model to account not only anisotropy but also the thickness component.